Boolean algebra is the foundational mathematics that support a lot of the things that we do in digital logic. So I'd like you to be able to take a look at Boolean properties and identities, take a look at an original expression, and understand how you can manipulate that mathematically to get a different form of that expression. So you might be asking, well, why would I want to do that? Well, I think one of the obvious answers is if I can simplify a Boolean expression, I can implement it with more efficient circuitry, fewer transistors, less power, probably faster switching speeds. All those things are important. So let's go through a few examples where we carefully apply the Boolean properties. I think this will be natural for you because you're so used to applying regular algebraic properties and then just adding in the little twist of, oh, this is Boolean, not regular algebra. It's not that hard to make those adjustments. But I do think it's also useful, both intellectually and just to know for sure why these things work, to take a look at reductions and identify from the property list exactly what happens. So I was going to step you through a couple of these, but if you go across the top, there's 5, 6 examples that you can take a look at and practice with. All right, so let's go through the first one. Let's say we had an original expression. Let's go to the next step and try to simplify this expression. So that's the goal. And so I think the first thing that we notice is that we have A ended with B, A ended with B bar. Algebraically, we can think of that as factoring out the A. The same thing works in Boolean algebra. Essentially, factoring out is an application in reverse of the distributive law. All right, so all this applies in Boolean algebra, and so we have this. Well, then we look at this and we say, oh, here's a Boolean identity, B or B bar. What I know about that, I can look it up on the list. That's the idempotent identity. A or A is equal to A. I'm sorry, that's the wrong one. What are we looking for? The complement property. A or A bar is equal to 1. And so we go to the next step and we replace that with 1, and that's true. All right. Then the next property is A or 1 is A. That one is so obvious it's hard to remember that you even applied a property. And so that is the next step. We would apply that as the identity law, and we get to a final answer that can result in a much simplified version of the same function. So Boolean algebra-wise, this is the same Boolean expression. Okay, let's do one more example. This one, I have it set up as an application of complements. And the reason I did that is because I worked through a previous example where we applied the pushing of bubbles through gates to get different forms of logic gates. That was an application of De Morgan's. And this is doing this process in reverse. So here's what I'm doing here. I'm applying an input, A bar, and another input, B, into a NAND gate. Okay, so you can see A bar ANDed with B with the bar here is the NAND. And then I'm going to AND those two, and that with this expression. So this is also a NAND gate. And then I'm going to NAND it at the end. So this is an all NAND implementation of a logic expression. Okay, so what we're going to do here is we're going to apply Boolean's property. Okay, so think of this as having a bar over the whole top of it. It's kind of tedious to code that into a graphic, so we just have a prime. So for the first step, we're applying De Morgan's, and De Morgan says if you take a product and you take the complement, it factors into basically changing the sign. Okay, but then applying the complement to each individual term. So these things broke up. A bar B broke up into a term with the bar on it, but then I had to apply another bar because this bar flows through. Okay, and so that's the first step. That's just an application of De Morgan's law. Okay, the next thing that we do is we do the double complement. So if I have a double complement, that just simplifies to A bar B, C, D. All right, so if you're remembering back, if you've already done that example, we did this with pushing bubbles through uh, regular ors and ands to come up with the way of essentially making the same kind of Boolean simplification. So that's the underlying supporting math for that process. All right, so I'm going to end this here, and what I'd like you to do is just play around with these examples, see if you can predict what the next property is in terms of simplifying. Make sure that you understand why each of these works. Get a little practice in, helps you develop your understanding of Boolean algebra.